Hello everyone, this is Revathy, Assistant Professor of Chemistry, Sri Sharada College for Women, Salem. I welcome you all for this session on aromatic electrophilic substitution reactions and the problems based on it. To understand the aromatic electrophilic substitution reaction, first we should know the basic concept about the structure of benzene. Here, the structure of benzene was shared here in the form of a picture. Here on each carbon it is having a p orbital which was perpendicular to the plane of the ring. The upper lobes of the ring are connected together to form a pi electron cloud on the ring. Similarly, the orbitals on below the plane of the ring are also connected together to form a ring below the plane. So, as a whole, the benzene ring was found to be like this in the form of a pi electron cloud above the plane as well as below the plane of the ring. In general, the aromatic electrophilic substitution reaction was found to be very slow, and also it leads to the formation of a substitution product but not the as usual addition product. Why it happens like this? Let us compare with alkenes. In general, in alkenes and alkyne, the addition reaction is found to be exothermic in nature, and also the reaction was found to be very fast and favorable because in this case a pi bond, a weaker pi bond is getting converted into a strong sigma bond and the reaction was found to be exothermic. But in case of electrophilic addition to the benzene ring containing C double bond C, it doesn't take place that much easily because the reaction was found to be endothermic in nature because it loses its aromaticity completely. It loses its aromaticity to give a product like this. So for this reason, the electrophilic addition across the double bond of benzene ring was found to be not possible in case of aromatic compounds as in case of alkenes and alkyne. And because of this pi electron cloud in the benzene ring, the benzene compound, that is aromatic compounds, are found to be more likely to undergo the electrophilic substitution reaction. Here, let us see what is an aromatic electrophilic substitution reaction. Here, the positively charged species which attacks the negatively charged pi electron cloud of the aromatic ring, where one of the hydrogen is substituted by an electrophile. This is known as electrophilic substitution reaction. In general, there is a negatively charged electron cloud which is lying above and below the plane of the ring. Electrophiles are, we know that it is a positively charged species and it is very prone to attack the negatively charged, the pi electron clouded aromatic ring. We expect that the aromatic electrophilic substitution reactions may take place very easily. But it is not the case because to preserve its aromatic character and its stability, it is very reluctant to use its pi electron. So the electrophilic substitution reactions in aromatic compounds, it takes place very slowly. Then let us see the mechanism of this aromatic electrophilic substitution reaction. Generally, it involves two steps. The first step is the formation of this rhenium ion. It is found to be slow step. Here, the aromatic compound, it loses its aromaticity and it becomes non-aromatic. That is, it forms a sigma complex. In this step, the electrophile, it accepts a pair of electrons from the benzene ring and it forms a resonance stabilized carbocation intermediate. It is known as rhenium ion or benzonium ion, Wieland intermediate or sigma complex, and it is found to be non-aromatic in nature, and also it is called as sigma complex because one of the pi electron is getting converted into sigma bond here. So we can call it as sigma complex as well for this resonance stabilized intermediate. And collectively this structure is known as rhenium ion. And this formation of rhenium ion is found to be a slow step, and it is also a rate determining step. When coming to the second step, the sigma complex, it loses a proton which can be abstracted by a base and it lead to the formation of a substituted benzene. Here what happens is the non-aromatic sigma complex, by the removal of a proton, it retains its aromatic nature. So it is found to be a fast step. So these are all the two steps involved in the mechanism of aromatic electrophilic substitution reaction. Here we are seeing the energy profile diagram for aromatic electrophilic substitution reaction. This is the diagram of potential energy versus progress of the reaction. The potential energy for the reactant was found to be more than the product. With the reactant, an electrophile just coming close together to form a bond. Here we can see that the electrophile is getting involved in bond formation, and then after that it forms a sigma complex and rhenium ion, that is known as rhenium ion. Once the rhenium ion is formed, look at the difference between the transition state and then this sigma complex. Here the bond is partially formed. Here we can see that the hydrogen is getting ready to removed from the rhenium ion. And then after the formation of sigma complex, this hydrogen getting a partially positive charged one. So once the rhenium ion formed, easily it goes to the second transition state, and then very easily and very fast rate of the formation of product as a substituted one. Look at the difference between the reactant and product. In reactant, it is hydrogen which is substituted by this electrophile, a positively charged species, to form a product E. That is the formation of electrophile substituted aromatic compound. This is regarding the energy profile diagram. Let us see the evidences for the formation of rhenium ion. There will be two evidences. First one is the isolation of rhenium ion intermediate. That means isolation of the sigma complex. When mesitylene is treated with ethyl fluoride in presence of BF3 at very low temperature, it forms a sigma complex. This sigma complex was isolated, and on further heating, it gives an electrophile substituted product. So this rhenium ion was easily isolated. This is number one evidence for the formation of rhenium ion. Number two is isotope effect. In general, in this mechanism, the rate determining step, it doesn't involve the CH bond breaking. So possibly there may be no isotope effect. For example, when deuterated benzene is subjected to nitration under similar condition, it doesn't show any primary kinetic isotope effect. That is, Kh by Kd is equal to 1. Now let us see the sigma and pi complex. Once the electrophile is getting intimate contact with the benzene ring, it is known as a pi complex. It forms a complex. Later on, it interacts with the pi electron cloud to lead to the formation of the sigma complex. After that, this H plus is getting ready to leave the aromatic system to provide a substituted benzene. So generally, one sigma complex and two pi complexes have been involved in the formation of a substituted benzene through aromatic electrophilic substitution reaction. Let us see the examples of aromatic electrophilic substitution reaction. The nitration is the first example we are going to see now. That is a reaction of an aromatic compound. For example, we had taken benzene here. The nitrating mixture is nitric acid and sulfuric acid. When nitric acid reacts with two molecules of sulfuric acid, actually it is act as a catalyst. It leads to the formation of hydronium ion and nitronium ion and anion also. So with this NO2 plus nitronium ion, we are able to synthesize a nitro compound. The mechanism of the nitration is found to be very similar to the general mechanism. Instead of electrophile E, we have to put NO2 plus. That's the matter of mechanism. Not only for the nitration, for the upcoming reactions also, like chlorination, bromination, and then alkylation, acylation, sulfonation. For all these reactions, we can follow the same general mechanism also. So where we used electrophile E plus, accordingly we have to use our electrophile for the concerned reaction, whatever we are using the concerned reaction. Here NO2 plus is an electrophile. It reacts with the benzene ring aromatic compound. It is found to be slow step. It provides the formation of rhenium ion or sigma complex. It is found to be non-aromatic because its aromaticity is lost while the formation of sigma complex. The second step is the sigma complex. From the sigma complex, a proton is abstracted by the base which is formed during the production of nitronium ion. The sulfate anion abstracts a proton from the sigma complex. provides the formation of a substituted compound which is found to be aromatic in nature. So not only nitrating mixture is not only this nitric acid and sulfuric acid, we can also use some other nitrating substance also. For example, concentrated nitric acid in presence of glacial acetic acid, dilute nitric acid alone we can use it, fuming nitric acid with the concentrated sulfuric acid, and fuming nitric acid with the fuming sulfuric acid, like that we can use. Similarly, we can use nitrogen pentoxide also. Here, in the production of nitronium ion, this nitric acid, it acts as a base and accepts a proton from a stronger acid, that is the sulfuric acid, and lead to the formation of nitronium ion. Let us see the next example, that is nitrosation. Here NO plus, nitrosonium ion, NO plus is produced by sodium nitrite and HCl. It gives sodium chloride and nitrous acid. This nitrous acid again react with the HCl to give this complex, and on further removal of water from this complex provides the nitrosation component. For example, phenol, it can undergo the nitrosation by using nitrous acid, which can be produced in situ by the reaction of sodium nitrite with mineral acid, sulfuric acid. At very low temperature, the NO group, nitrosonium group, is introduced into the phenolic compound. The next example is diazo coupling. Here the electrophile is benzene diazonium ion. It is found to be less reactive nitrogen electrophile. It readily attacks the highly activated aromatic rings to provide the corresponding dye. This is the basic reaction of our analysis of phenolic compounds as well as the amine compound. This diazonium salt easily react with the phenol in presence of basic medium at very low temperature 0 to 5 degrees Celsius. Easily it provides the formation of a red dye, para-hydroxyazobenzene in this case. The next example we are going to see is bromination and chlorination. Similarly, iodination and fluorination also we can see in further slides. For chlorination, we have to use chlorine molecule along with an ion to provide FeCl3, which is a Lewis acid. So, a reaction of benzene with the halogen molecule in presence of that concerned Lewis acid ferric chloride, it provides halobenzene. Similarly, for bromine molecule in presence of FeBr3 Lewis acid, it provides bromobenzene with good yields. While coming to the mechanism, bromine molecule react with FeBr3 Lewis acid. Here, the bromine molecule itself acts as a Lewis base. FeBr3 acts as a Lewis acid to provide the formation of a complex, that is Lewis acid base complex. This complex reacts with the benzene ring to form an arenium ion. This arenium ion is resonance stabilized. While the formation of arenium ion, we are getting FeBr4 minus 2. This anion abstracts a proton from the sigma complex to lead to the regeneration of our Lewis acid, which we had used initially at the first step for the formation of complex. So this Lewis acid is getting regenerated. So this FeBr4 minus abstracts a proton. It provides HBr and regeneration of catalyst, and also our expected and targeted product bromobenzene. Similarly, we can do for chlorination also. These are all the examples for bromination as well as the chlorination. While brominating simple monohydric phenol, it gives tribromophenol, white solid. Similarly, upon bromination of aniline, it gives tribromoaniline, white solid. So from this base reaction, we can estimate how much phenol is given to our unknown sample. So through estimation, we can find out the quantity of phenol or quantity of aniline which we had in the unknown solution. Similarly, for chlorination also we can do. So chlorination of phenol by using chlorine water, it gives trichlorophenol, and similarly for aniline it gives trichloroaniline. And the next example is iodination. Here the iodine in aromatic compound, the substitution of iodine in aromatic compound is not that much easier as in case of chlorine and bromine, because it is found to be, the iodine is found to be very least reactive among the halogens. So the reaction may be reversible in nature. So for doing iodination, it requires an oxidizing agent such as nitric acid, or in some cases we can use hydrogen peroxide in presence of a sulfuric acid. Here nitric acid we are using. In presence of sulfuric acid and the iodine molecule, it provides iodinium ion which react with the benzene ring molecule to provide the iodobenzene. Similarly, we can do fluorination also, but direct fluorine molecule substitution is not that much easier, because fluorine was found to be very reactive. So direct fluorination is not feasible at all at normal room temperature. So we have to we have to substitute fluorine indirectly by using the reaction that is known as Sheeman reaction. Here we have to heat the benzene diazonium borofluorate complex. It provides the formation of fluorine substituted compound. So these are all the examples of bromination, chlorination, iodination and halogenation. Here we can see the another example of aromatic electrophilic substitution reaction is sulfonation, that is substitution of SO3H. That is a conversion of benzene to benzene sulfonic acid by using concentrated sulfuric acid at a higher degree Celsius, or we can use fuming sulfuric acid at room temperature or 25 degrees Celsius. Here, when sulfonation takes place, unlike the other electrophilic substitution, the sulfonation reaction was found to be reversible in nature, which we can see in further slides. Here, during the production of an electrophile, SO3 is the electrophile. This SO3 itself can act as an electrophile, or it may get protonated. The protonated form of SO3 also can act as an electrophile. Here, this is the first mechanism is representing the protonated SO3. When using this as an electrophile, we are getting the benzene sulfonic acid. Similarly, when using sulfur trioxide alone as an electrophile, here also we'll be getting the benzene sulfonic acid. Mechanism is also found to be similar. The only thing is both protonated form of sulfur trioxide as well as sulfur trioxide can be used as an electrophile for substituting SO3H in the benzene ring. Now let us discuss the difference of sulfonation from the other aromatic electrophilic substitution. How it get differentiated from the others? Because it undergoes desulfonation. In the previous slide, we had seen that while using concentrated sulfuric acid, benzene is converted into benzene sulfonic acid. The same benzene sulfonic acid is get back to its benzene while using dilute sulfuric acid. So both the reactions are found to be, that is, the sulfonation is found to be in equilibrium. That means it is found to be reversible. Benzene on reaction with the corn sulfuric acid, it provides benzene sulfonic acid. This benzene sulfonic acid with the dilute sulfuric acid, it get back to its reactant benzene. So the sulfonation was found to be reversible. This is the only case found to be reversible in aromatic electrophilic substitution reaction, but not the other reactions. And the next thing is, this sulfonation reaction shows kinetic isotope effect. And when coming to the desulfonation, here we should consider the principle of microscopic reversibility. The mechanism also was found to be the reversal of sulfonation mechanism. Hence, desulfonation is an electrophilic aromatic substitution where the electrophile is found to be proton. And the second thing is sulfonation. It shows a kinetic isotope effect. So we can compare the sulfonation of benzene and deuterated benzene. Similarly, the nitration of benzene as well as the deuterated benzene here. It shows that sulfonation itself shows the isotopic effect. Kh by Kd value is found to be 2. So from the reversibility of the reaction, it becomes clear that activation energies in returning to the intermediate to the reactant, that is, the activation energy for get back to its reactant as well as getting converted into product was found to be same or almost equal. But this is not in the cases of other electrophilic substitution reaction like nitration, halogenation, etc. In general, the intermediate requires very less energy to convert into products. This is in case of the nitration and halogenation, etc. But it is not in case of sulfonation. Here we can see and we can observe that both the energy level for get back to its reactant or for the converting into product is found to be, the energy level was found to be almost equal. Hence, from the profile diagram, we can say that the sulfonation was found to be reversible in nature also, we can say that. And in case of deuterated benzene, it is found that still more energy is required to convert into product than the normal benzene. It means deuterated benzene requires higher energy to convert into product than the non-deuterated benzene for sulfonation reaction. When comparing with the nitration reaction, nitration for non-deuterated benzene is found to be very easy, and for deuterated benzene is also found to be somewhat easy, because the energy level for both non-deuterated as well as the deuterated benzene was found to be less than the intermediate, less than this. So, the sulfonation reaction was found to be reversible as well as it shows the kinetic isotope effect. Let us see the example of sulfonation of naphthalene. Here we should know what is kinetic control and what is thermodynamic control. When the reaction produces more than one product, which means the product which formed most readily is said to be kinetically controlled product or kinetic product. The reaction which produced that kinetic product is said to be kinetically controlled reaction. In case of thermodynamic control, the product was found to be more stable. That stable product is called thermodynamically controlled product or thermodynamic product. And the reaction which produces the most stable product as a major one is said to be thermodynamically controlled reaction. Let us see the kinetic versus thermodynamic control by taking naphthalene as an example, that is sulfonation of naphthalene. While doing the sulfonation of naphthalene by using concentrated sulfuric acid at 80 degrees Celsius, we are getting 1 naphthalene sulfonic acid. The same reaction and the same reagent, but the temperature was found to be higher, that is at 160 degrees Celsius. It provides 2 naphthalene sulfonic acid as a major product. The sulfonation reaction was found to be readily reversible at elevated temperature, that is at higher temperature. But at low temperature it is found to be irreversible. And then the rapid formation of this 1 naphthalene sulfonic acid is due to the greater stabilization of that arenaceous ion intermediate formed. And at during the formation of 1 naphthalene sulfonic acid, the arenaceous ion which contains, the resonance stabilized arenaceous ion which contains 2 structures, the 1 and 2, it contains, this ring is having the positive charge. And in case of beta substitution, that is during the formation of 2 naphthalene sulfonic acid, it contains only one structure. The structure is 6. Because in case of 1 naphthalene sulfonic acid formation, this structure 1 and 2 only it retains its aromatic character. But the other structures 3, 4, 5, both the rings have lost its aromaticity in here. In case of 2 naphthalene sulfonic acid substitution process, the structure 6 only retains one of its ring is having its aromatic nature. But all the other structures 7, 8, 9, 10, all of them lost its aromaticity in both the rings. Since alpha acid is found to be thermodynamically less stable than the beta acid, even though alpha is formed more rapidly. While considering the steric hindrance of the sulfonic acid group at C1 position of naphthalene, it gets hindered with the hydrogen of peripheral, that is at C8 position. So the alpha naphthalene sulfonic acid, 1 naphthalene sulfonic acid is found to be less stable because of that steric interaction. When coming to the 2 sulfonic acid, it is not having that much interaction, not that much steric hindrance among these adjacent hydrogen. So because of that, it is found to be 2 naphthalene sulfonic acid was found to be most stable thermodynamically controlled product. When coming to the energy profile diagram, we can observe that at higher temperature, the major product is 2 naphthalene sulfonic acid. Under equilibrium condition, the less stable product, that is 1 naphthalene sulfonic acid, it readily undergoes desulfonation to yield naphthalene, which undergoes further attack at C2 position, that is at beta position, to give a more stable 2 naphthalene sulfonic acid as a thermodynamically controlled product. So from the profile diagram, we see that the 2 naphthalene sulfonic acid was found to be stable, thermodynamically controlled product. Let us see the next example of aromatic electrophilic substitution reaction as Friedel-Crafts alkylation. That is a reaction of an aromatic compound with an alkyl halide in presence of a Lewis acid. It gives an alkyl substituted benzene. That is a production of alkyl benzene. Here, our alkylating agent itself acts as a Lewis base. It reacts with the Lewis acid, aluminum chloride. It provides a complex formation. This complex interacts with the benzene ring to form an arenium ion, a sigma complex, and also an anion, AlCl4-. This anion abstracts a proton from the sigma complex to get back to its Lewis acid catalyst and also an alkyl substituted benzene compound, that is an alkyl benzene. Here, there are some limitations for this alkylation reaction. First one is polyalkylation. What is that polyalkylation? Bromination, nitration, sulfonation, we had seen that. Once these groups are introduced into the benzene ring, the product obtained is found to be less susceptible for further electrophilic attack. But in case of an alkyl benzene, it is found to be the product formed, that alkyl benzene formed is found to be more prone for the alkylation rather than the normal benzene. Hence, polyalkylation can occur. This is one of the limitations. And the rearrangement of less stable carbocation. We know that tertiary carbocation was found to be more stable than the secondary than the primary. In case of formation of primary carbocation, it gets rearranged itself to get to secondary carbocation, and that secondary carbocation is attacked on the aromatic ring to give a substituted product. This is the another limitation. And the third one is the Friedel-Crafts alkylation reaction is not possible with the substrates which having -I minus R group as well as the plus R group, because the strong electron withdrawing nature groups like CF3, NO2, CN, aldehyde group, ketone group, acid group, these groups actually deactivates the aromatic ring and it doesn't allow the substrate to undergo Friedel-Crafts alkylation reaction. But in case of plus R group, these are all found to be very strong activating group like amine, NHR, NR2, like these compounds, like these functional groups, it forms a complex with the Lewis acid. So once the complex is formed, that complex is found to be electron withdrawing in nature, that is deactivating complexes is formed with plus R group. Similarly, aryl and vinyl halides cannot be used instead of alkyl halides. Another example of aromatic electrophilic substitution is Friedel-Crafts acylation reaction. That is, an acyl group is introduced into the aromatic compound. For example, a reaction of benzene with an acid chloride, or it may be called as an acyl chloride, in presence of a Lewis acid AlCl3, an acyl group is substituted here, that is, a ketone is formed. The acyl halide react with the Lewis acid, it forms Lewis acid base complex. The complex get dissociated to form an acylium ion. This acylium ion was found to be resonance stabilized. This acylium ion attacks the benzene ring. It forms a sigma complex arenium ion, and the formation of this AlCl4 minus, this base abstracts a proton from the benzene ring. It gets converted into a ketone compound, that is an acyl group substituted aromatic compound. Here, as in case of alkylation, the polyacylation rearrangement is not at all a problem for acylation. It is also found to be irreversible in nature. And the one thing is, the bulky groups, the crowded bulky acyl group goes to the less crowded position of the benzene ring. As of now, we had seen that what is the structure of benzene, what is electrophile, what is aromatic electrophilic substitution reaction, the general mechanism, evidence for the formation of arenium ion, and examples for the aromatic electrophilic substitution reactions like nitration, nitrosation, diazo coupling, bromination, chlorination, alkylation, acylation. We had seen that. Hereafter, we are going to see the problems based on the aromatic electrophilic substitution reaction. Our first problem is, how would you synthesize the following? That is, how would you synthesize N-ethyl benzene from aniline? So for that, we can do the N-acylation. Aniline is acylated to give acetanilide, and then on further reduction by lithium aluminum hydride, the CO group, carbonyl group, is getting converted into CH2. So the easiest conversion, that is the preparation of N-ethyl benzene from aniline. And the next conversion is metabromotoluene from benzene. So we should know the structure of our expected product. Then only we can able to follow the steps. Which step we have to be followed, we have to know. So for that conversion, benzene is first alkylated to give a toluene, and on further nitration it produces paranitrotoluene, and further reduction with this tin and HCl, this NO2 is converted into, that is reduced to NH2, and on further acylation this amine part is get converted into anilide, and on further bromination it provides bromo group is getting introduced ortho to the anilide functional group, because both NHCOCH3 as well as the methyl group was found to be orthopara-directing. When comparing these two orthopara-directing groups, anilide functional group was found to be dominant one. It decides the incoming electrophile bromonium ion where it has to be go. So depending upon the position of anilide, it decides the incoming bromonium ion. It goes to the ortho position to the anilide. And then after the introduction of bromine to the ortho position, similarly it is meta to the methyl group, which on further reaction with the con HCl, this anilide group is getting converted into amine. That amine is treated with the sodium nitrate and HCl. It converted into diazonium salt, which on treatment with the phosphorus salt, it gives metabromotoluene. Next, let us see how we can synthesize phenanthrene and tertiary butyl benzene from benzene through Friedel-Crafts acylation. Benzene is treated with an anhydride. This is an aliphatic succinic anhydride. It can be used as an acylating agent. In presence of aluminum chloride, it gives an acylated product, which on further treatment with polyphosphoric acid and concentrated sulfuric acid, this open chain acid functional group is get converted into a cyclic ketone, which on further reduction with zinc amalgam and HCl, that is the Clemmensen reduction, this keto group was converted into an alkane, followed by the aromatization. It renders naphthalene formation. And again, reaction of succinic anhydride in presence of aluminum chloride, it further undergoes the acylation reaction at the C1 position of the naphthalene to provide this open chain compound, and we had cyclized through PPA and sulfuric acid, that is polyphosphoric acid and sulfuric acid. A cyclized diketone is obtained, and further Clemmensen reduction and aromatization, we obtained phenanthrene as a product. This reaction is based on the Friedel-Crafts acylation reaction. And then we can see here how tertiary butyl benzene is produced from benzene through Friedel-Crafts acylation reaction. This tertiary acyl halide is get converted into tertiary acylium ion, followed by the elimination of carbon monoxide. It gives tertiary carbocation. It is found to be more stable, which react with the benzene to give an alkylated product. Okay, this is a alkylation reaction. Okay, so we have to introduce an alkyl group. This tertiary butyl group is an alkyl group, but when we had when we are taking tertiary butyl halide instead of this acyl halide, it gives polyalkylation. To overcome that polyalkylation, this tertiary acyl halide we had used, and later on it provides acyl ion, and on further elimination of that CO, it provides tertiary carbocation. Immediately it reacts with the benzene ring to produce tertiary butyl benzene as our product. Here the question is, we are provided with the compound name and structure. We have to determine where the incoming electrophile is getting substituted. So we have to indicate the position. The first compound is phenyl benzoate. It contains 2 benzene rings and 1 C double bond O group, that is an ester group. So we have to identify in which phenyl ring the incoming electrophile goes to. When we are looking for this benzene ring, it is having a C double bond O group. It is found to be an electron withdrawing in nature. So it is not possible for the incoming electrophile that much easily. So when coming to this benzene ring, it is attached with an O. So it is electron donating in nature to the benzene ring. So it is, as it is an electron donating in nature, ortho to this position, that is both ortho as well as para to this position. The positions are indicated here. To this position, the electrophile can undergo the substitution reaction. The next example is orthonitro-toluene. Here we have 2 groups in a benzene ring. One is methyl, the second one is NO2. When 2 groups are there in the benzene ring, one is an electron donating group and the other one is electron withdrawing group, means the incoming electrophile is predicted can be carried out, can be dominated by the electron donating group. So according to the position of this electron donating group, the incoming electrophile can go. So the position of this, based on this electron donating group, it goes to the ortho as well as the para position. Here we have to find out the incoming electrophile position for the metamethoxytoluene. Here both the groups are electron donating group. So what can we do here? We have to find out which one is more activating, more strongly activating. When comparing these two, the methoxy substituent was found to be more activating. So according to methoxy position, the incoming group can go to ortho to methoxy at this position only, not here. Even though it is found to be ortho, it is in between the 2 bulky groups, that is methoxy as well as the methyl group. The incoming electrophile, because of steric hindrance, it doesn't go here. It goes to this ortho position as well as para position. It is ortho to methoxy as well as para to methoxy. The next compound is salicylic acid. This is the structure of salicylic acid. Here COH is found to be deactivating group and OH is found to be activating group. So when both activating as well as deactivating in the same ring, the activating, based on the activating group, the incoming electrophile goes here according to OH, ortho to OH as well as para to OH, the incoming electrophile can go here. And the next example is styrene. This is the new case to predict the incoming electrophile. Here in the benzene ring, we are having an alkene, CH double bond CH2. We have to take it as an alkyl substituted. So according to that, So ortho to this alkyl substitution here as well as para to this position, the incoming electrophile can go. And the next question is, how do you synthesize metabromoethyl benzene from benzene? So this question, so all this metabromoethyl benzene, paranitrobromobenzene, metatoluene, all these things we have to be synthesized from benzene. So first compound is metabromoethyl benzene. This can be prepared via acylation. First we have to do the acylation. What kind of acyl halide we can use? We can use acetyl halide, because while using the acetyl halide, an acyl group CH3CO group is substituted here, and on further reduction it gives an ethyl group. To overcome the polyalkylation, while using ethyl chloride, it undergoes the polyalkylation. So to avoid that polyalkylation, first we did the Friedel-Crafts acylation, then our need of introduction of bromine group in our needed position, as the acyl group is a strongly deactivating group and meta-directing group. It allows the incoming electrophile bromonium ion to the meta position to this acyl group. So we had obtained metabromo acetophenone, and on further Clemmensen reduction it gives metabromoethyl benzene. So like this we can prepare an alkyl benzene through acylation reaction, but not the direct alkylation, because it could lead to the polyalkylation reaction. And the second expected compound is paranitrobromobenzene from benzene. First we have to brominate it. Bromine group is introduced, and then nitric acid, sulfuric acid combination. It provides a nitronium ion. It undergoes a nitration reaction. So it provides nitro group can get introduced para to the bromo group, because this halogen was found to be deactivating, but it is ortho-para directing. So the compound is para substituted nitro compound. If we are doing the nitration first, we are obtaining the nitrobenzene. That NO2 group is found to be a meta-directing group, and on further bromination it provides metabromo-nitrobenzene, not our expected paranitrobromobenzene. So we have to decide which process has to be carried out first, either bromination or nitration. That sequence we have to be very clear about that. And the third compound is, we have to prepare metatoluene from benzene. Here we can first nitrate the benzene to provide the nitrobenzene, followed by the alkylation. It provides metanitrotoluene, and on further reduction with tin and HCl, it provides metatoluene. And we have to synthesize paratoluene also from benzene. Similarly, as in case of metatoluene, we have to alkylate first and then nitrating it. So benzene, for alkylation, it gives alkylated toluene, and on further nitration it gives paranitrotoluene, which on further reduction with the tin and HCl, it provides paratoluene. So from this paranitrotoluene, we can able to synthesize 2-bromo-4-nitrobenzoic acid. By means of bromination, we can get incoming bromonium ion ortho to the methyl, because methyl is ortho-para-directing, activating. NO2 is meta-directing, deactivating. So when both the deactivating and activating are there in the group, the incoming electrophile is based on the nature of electron donating group. So ortho to the methyl position, a bromonium ion gets substituted, followed by oxidation, a side chain oxidation. Whatever may be the alkyl group in the side chain of benzene ring, which on oxidation it gives acid as a functional group. So At last we had obtained 2-bromo-4-nitrobenzoic acid from benzene. And here we are going to synthesize 1,3,5 tribromobenzene from benzene. Here first we have to nitrate it by using nitric acid and sulfuric acid. Nitrobenzene is obtained, followed by tin HCl reduction. It gives amine as a product, that is a primary amine, aniline, followed by bromination. It gives a tribromoaniline. Recently we had seen in the case of bromination examples, we had seen the bromination of aniline. It gives tribromoaniline, white solid. Which on treatment with the sodium nitrate and HCl, this amine group is getting converted into diazonium salt, which on treatment with phosphorus salt on heating, it provides the diazonium salt is, this nitrogen is getting eliminated as nitrogen gas. So at last we had obtained our targeted product, tribromobenzene. Here we have to synthesize para-bromoaniline from benzene. There are two possible ways. From benzene, we have to nitrate it first. Nitrobenzene we had obtained. Reduction by tin HCl. Aniline, primary amine is formed. It has to be acylated. That is, N-acylation has to be done. Anilide is formed, followed by bromination. As it is the orthopara-directing group, para-bromoacetanilide is formed as a major product, which is followed by hydrolysis, acidic hydrolysis. This anilide group is converted into para-bromoaniline. This is also, in this way also we can do the synthesis. The other way to synthesize para-bromoaniline is bromination of benzene. It provides bromobenzene, followed by nitration. It gives para-nitrobromobenzene, followed by tin HCl reduction. This NO2 is reduced to amine. So this type of preparation also be done, and we have to synthesize orthobromotoluene from benzene. Benzene, it is alkylator to give toluene. It reacts with the concentrated sulfuric acid. It provides SO3H is introduced to the para position of CH3, followed by bromination. Here methyl group is orthopara-directing, SO3H is found to be meta-directing. So according to methyl group ortho position as well as meta to the sulfonic acid group, here this position is getting brominated, followed by dilute acid treatment. It gets desulfonated to provide orthobromotoluene. Already we had studied in the sulfonation reaction. While using the concentrated sulfuric acid, sulfonic acid group was introduced. It was substituted in the benzene ring. While using dilute acid, the sulfonic acid group was getting desulfonated. So this is one of the application for introducing an electrophile to the required positions. Later on we can remove the sulfonic acid functional group by using dilute acids. This is one of the application of the sulfonation reaction also. And the next conversion is metachloroethyl benzene from benzene. Here we have to prepare ethyl benzene. So we have to introduce ethyl group. Directly if we are using ethyl chloride as an alkylation reaction, it gets polyalkylation as a limitation. So there is a limitation that the polyalkylation is happening in the case of alkylation. So we have to do the acylation. So acyl group is introduced. We are getting acetophenone as a product, which on treatment with the chlorination and FeCl3, that is chlorination reaction is happening here. As it is the meta-directing group, meta position, in the meta position chlorine is getting substituted, which are followed by reduction with zinc amalgam HCl Clemmensen reduction. The keto group is converted into CH2. So the COCH3 is getting converted into CH2CH3. So the required metachloroethyl benzene is prepared. And the next conversion is orthobromophenol from phenol. So in case of phenol, upon sulfonation, it gives disulfonic acid, ortho to OH as well as para to OH group, which are followed by bromination in presence of a base, sodium hydroxide. It gives bromonium ion as well as this OH is converted into phenoxide, sodium phenoxide anion, which on treatment with dilute acid, both SO3 groups get desulfonated to give the required orthobromophenol or expected product. It has been synthesized from phenol. And here we are going to prepare orthonitroaniline as well as the paranitroaniline. For that, benzene is first nitrated. It provides dinitrobenzene. Actually, it should first mononitration as well as the dinitro compound will be formed, which on further reduction with ammonium sulfide, it gives one of the NO2 only get reduced. That is, metanitroaniline has been formed. In case of benzene on nitration, first it forms a mononitro product followed by reduction. Aniline is formed, followed by N-acylation, acid anilide is formed, which on treatment with the nitration, that's nitrating mixture, it provides paranitro-acetanilide, followed by hydrolysis. This anilide group is converted into amine. So we are getting paranitroaniline. Similarly, from the anilide functionality, we can sulfonate here by using the concentrated sulfonic acid. SO3H is introduced para to the anilide functional group, and on followed by nitration, only position has to take place at ortho to anilide functional group. This position is also meta to SO3H. At this position, NO2 was substituted, followed by dilute acid reaction. This SO3H was removed. That is, desulfonation is taking place, and also anilide is getting converted into amine. So we had synthesized orthonitro-aniline as a product. So from benzene we had prepared orthonitro-aniline, paranitro-aniline as well as the metanitro-aniline based on the nitration and acylation reactions. Here, how we can prepare orthonitrobenzoic acid, metanitrobenzoic acid, paranitrobenzoic acid from benzene. So benzene should be alkylated first. We should be prepare the benzoic acid derivative. So for obtaining the benzoic acid, that is acid functional group, there should be a side chain. It may be an alkyl. So the alkyl group was introduced by alkylation of benzene. We are getting toluene as a product, which on oxidation it gives an acid, that is benzoic acid is formed, followed by nitration with nitric acid and sulfuric acid. It gives metanitrobenzoic acid, as the acid functional group is found to be meta-directing group. When the toluene is nitrated, it provides a mixture of orthonitrotoluene as well as the paranitrotoluene, and on both these compounds on further oxidation it provides the corresponding orthonitrobenzoic acid as well as the paranitrobenzoic acid. So we had coming to the end of the session. First part of the session we had seen what is the general concepts of benzene, electrophile, aromatic electrophilic substitution and the corresponding aromatic mechanism, and for the examples nitration, halogenation, alkylation, acylation, sulfuration we had seen, and in the second part we had seen the problems based on this aromatic electrophilic substitution reaction. So we had synthesized many compounds based on the application process. Thank you. Is there any questions?